go ahead and start the recording. And I can start introducing Jason. So everyone, welcome to the penultimate Astro Colloquium this semester. So today we're very pleased to have Professor Jason Dexter from the University of Colorado at Boulder. Jason got his PhD from University of Washington in 2011. After that, he was a postdoctoral prize fellow at Berkeley, and then a junior research group leader at MPE Garhin, before joining the faculty at CU Boulder in 2019. So Jason has won a long list of prestigious awards, and I will only just mention a few most recent ones, which include an Alexander van Humboldt Award, the 2020 Breakthrough Prize in Fundamental Physics shared with the Event Horizon Telescope collaboration, and most recently a 2020 Alfred Sloan Research Fellowship. Jason studies the observational properties of gas falling onto black holes and their use as probes of strong gravity. He works on both series observations from the hardcore numerical calculations of accretion flows to hands-on reduction and analysis of observational data. And he's one of the few people I know who work both on the Event Horizon Telescope and VOT's gravity instrument. Both are very powerful facilities to explore the small-scale structure of accreting supermassive black holes. And today, Jason will talk about magnetic fields near the event horizon of Sgr A and M87 supermassive black holes from polarized black hole images. So Jason, please take that away.
Okay, great. Yeah, well, thanks for the very nice introduction and the opportunity to talk today. Thanks to everyone for coming. So today I'm going to present some new results about event horizon scale polarized images and try to convince you that that's a really great way to see basic processes related to accretion and jet launching next to a black hole event horizon. And as Yue said, I'm part of two large collaborations carrying out these measurements. And so this talk today is on behalf of the Event Horizon Telescope and VLTI Gravity collaborations. I've listed on the slide graduate students and postdocs that I've worked with. The colored fonts are for people that I have supervised, and the others are talented junior scientists in the Event Horizon Telescope collaboration that I worked with on trying to understand what we're seeing in this bottom swirly pattern, the M87 image, but now with linear polarization. And so we'll talk about that today. Okay, so the basic premise of the talk is that we see black holes in the universe via their gravitational influence on surrounding gas and stars, and also by light radiated very close to their event horizons, like in the cartoon of an accretion disk on the left, or by their launching of relativistic jets shown in the image on the right, where those jets can even propagate out to scales of galaxies and potentially influence the surrounding host galaxy. And both of those basic processes of accretion, growth of black holes by feeding on gas, and jet launching are thought to critically be reliant on magnetic fields in the hot plasma around the black hole. Okay, and so the basic question that I want to address today using black hole images is, what is the role of magnetic fields in these processes? What can we learn about how magnetic fields drive accretion onto central objects and launch relativistic jets? Okay, and so we will use that. We'll do that using black hole images. So my plan is first I'll introduce the theory of this, how we think that this might work, and the theory that we would like to test based on MHD simulations of accretion. And then I'll discuss black hole imaging results and talk about the new polarization results. And so I'm sure some people are much more familiar with this than others. Please feel free to interrupt with questions at any time. And I don't know if it'd be useful, but we could also stop halfway through if you think that would be useful, or otherwise wait till the end, but I'm happy to answer questions at any time. Okay, so the basic idea of why we think magnetic fields are so important in accretion is that a hot plasma with a weak initial field that starts a differential rotation in the sense of Keplerian rotation is unstable, and that process saturates in turbulence, and that turbulence drives stresses which allow the gas to lose angular momentum and fall into the middle. So this is what actually allows accretion to proceed, allows gas that's hung up in rotation to lose its angular momentum and fall inwards. Okay, and so the recognition that this can work as a robust mechanism for allowing accretion to proceed was a great achievement in the field. And it lets us do physical calculations of black hole accretion. The downside is that immediately this is turbulence, so we need 3 spatial dimensions to accurately model it, and it's time dependent. And if we care about going close to a black hole like today, then we also need the black hole spacetime in the problem. And so this quickly becomes a large-scale computational problem to try to do this type of accretion theory. So the method that we do for this, pioneered in part in Illinois, is called GRMHD, or general relativistic magnetohydrodynamics. So there's a fixed black hole spacetime. The black hole is drawn here in a coordinate map with the vertical direction here and the radial direction here. And so the spacetime is fixed, and then we solve the equations of MHD on a grid. So starting from some initial distribution of gas, then seeded with magnetic field, this becomes unstable. And this is the log density where you can see there's turbulence, and gas actually falls into the middle here. Okay, so we can do accretion theory in this way on the computer, physical realization of accretion theory. And this is just a movie of a 3D model of this, just as an example, where again, this is the vertical direction here. And now we've shown magnetic field lines in this, just to demonstrate that we also launch relativistic jets, so Poynting flux dominated jets from the spin axis of the black hole, if the black hole is spinning. Okay, so these are the field lines defining the boundaries of the jet. In this mostly evacuated region, the darker purple colors here, low density, magnetically dominated material driving a jet outwards. Okay, so one more statement on this is that currently there are sort of 2 major categories of how we think that this process can actually work. And it depends on an initial condition. So we start with an initial distribution of gas around a black hole. We are not currently, for the most part, modeling the feeding of the gas all the way out from some much larger scale. And so the result that we get in the end depends on at least how much magnetic flux, how much vertical magnetic field we put in the initial distribution of gas. And 2 qualitatively different states seem to form from this that we can realize. One of them is kind of the way this was done mostly in the past, which has weaker initial magnetic fields. And so the magnetic fields here, the strength of the magnetic fields saturate before they become in equipartition with the plasma. So we call these weaker magnetic fields, or sometimes these are referred to as sane models of accretion. And on the right is the other limit, where you put so much flux on that it actually saturates on the black hole. And this results in a qualitatively different type of accretion flow, where the magnetic fields become dynamically important and they can resist inflow. And this model here, because it has the maximum value of the flux, drives the strongest jets. Okay, that's related to both the black hole spin magnitude in the Blandford-Zanac mechanism and the magnetic flux that's present near the event horizon of the black hole. Okay, so this is the accretion theory that we would like to test. And specifically for today, we will try to learn about magnetic fields near the black hole and whether they are dynamically important or not. So we'll try to use the first results to get at that question, at least in a couple of objects. All right, so what we do to compare these simulations to observations is that we take the simulation data, ideal fluid data, like shown here in a coordinate frame, and then we need to calculate what these should look like at wavelengths we can observe, which tends to be in the submillimeter or up through about the infrared. And the advantage of doing this type of modeling with MHD simulations, I think, is that they are already time dependent and fully relativistic. And all accreting black hole sources are variable in time. And they also self-consistently evolve the magnetic fields, which give rise to the synchrotron radiation, which we observe from low luminosity accretion flows. So the targets of relevance today are the Galactic Center black hole, Sagittarius A star, and M87. And both of those sources are very sub-Eddington. So you can see here I'm listing typical plasma parameters, an electron temperature or equivalently energy. So these are like mildly relativistic near the event horizon, very low density, and relatively strong magnetic fields compared to the density. And the very low density and high temperature here are why we care about synchrotron radiation, and why the polarized radiation that we see will end up telling us something about the magnetic fields near the event horizon. Okay, so this right plot is showing then a synchrotron emission map from Monika Mostrzebatska that's showing that the emission is concentrated at the wavelength where the Event Horizon Telescope observes 1 millimeter, is concentrated very close to the black hole. So actually in our computational domain. And so we can calculate images of what these accretion flows should look like and then compare them with observations. Okay, so we do that using a ray tracing radiative transfer technique. I'm sure most of you have seen images like these. Just as an example of a movie that we get from this, the colors here are false color total intensity at 1 millimeter, and the white ticks that we will look at a lot today are our linear polarization magnitude is the length of the tick in these plots, and then its direction is the linear polarization direction of the electric field, the EVPA. Okay, and so we end up the MHD accretion theory that we've discussed ends up predicting for those two sources that we should see images that look kind of like these. So these images tend to show ring type shapes. They are more often than not brighter on the left side in this picture, the rotation where the gas is coming towards us due to the Doppler beaming effect. And the central region that's dark here is known as the black hole shadow, caused by relativistic effects of light bending and gravitational redshifts. Okay. So by calculating these types of images, we can then basically compare them to observations and answer basic questions like, do observed black hole images look anything like what theory predicts? And then today I'd like to go one step further and try to actually learn something about what these magnetic fields are doing near the black hole. Are they dynamically important or not? Okay, great. So there are two experiments that can do these observations and get at kind of this information in a new way. So actually resolve the emission from near the event horizon and basically try to go down to scales of the event horizon and see what magnetic fields are doing right next to a black hole event horizon. And so I'll talk about two of these today. The first one that I'll talk about is the Very Large Telescope Interferometer instrument called Gravity, which combines the light from 4 8 to 10 meter class telescopes and 8 meter telescopes in Paranal, and operating at a near infrared wavelength of 2 microns. This gives a virtual aperture of the telescope that's roughly 100 meters or 120 meters. And so an imaging resolution which gets down to sort of milli-arcsecond scales. Okay, so this is the animations, for example, of stellar orbits in the center of our galaxy are done with single 8 to 10 meter class telescopes with adaptive optics. And so this is roughly a factor 15 improvement in the imaging resolution that we can immediately achieve by doing the interferometer. And the breakthrough of the Gravity instrument is being able to do this on faint sources. Optical interferometry has traditionally been limited to, say, stars, brighter objects. And then we can now go to faint objects like, say, the black hole in the center of the galaxy, Sagi star. Okay, but still, if you ask what is the size of the event horizon of Sagi star or M87 on the sky, it's way smaller than this 4 milli-arcsecond number. It's more like 10 to 100 micro-arcseconds. It's incredibly small spatial scale, even for the two targets which are chosen to be the largest event horizons on the sky. Okay, so what we'll do in this case of the Gravity instrument, we won't make resolved images of a black hole, but instead we can do astrometry much more precisely than we can image. And so we can actually track the motion of the emission region as a function of time, very similar to what's been done for stellar orbits, but now on timescales of minutes and with spatial scales of tens of micro-arcseconds. Okay, and the second one that I'll talk about is the Event Horizon Telescope, where combining 1 millimeter observing facilities all over the Earth with sort of 10,000 kilometer scale baselines, and this produces then an imaging resolution which actually is sufficient to make resolved images of black holes. Okay, and the big advance here was the inclusion of more stations, and in particular ALMA, which lets this become an imaging array, rather than the pioneering earlier observations, which could detect compact flux but couldn't make resolved images. Okay, so I'll talk about the first results from gravity first, and then the EHT. All right, so gravity is a European consortium led in MPE Garching, where I used to work. And again, is a large collaboration focusing on faint optical interferometry. So interferometry of fainter sources than was previously possible. And so for the Galactic Center science case that I'll talk about today, there's a lot of science enabled by gravity, from AGN to exoplanets. And I'm happy to answer questions about it, but I'll focus on the Galactic Center case today. But in the Galactic Center case, what this looks like is that in the past, if you've looked very, very, very close in, so on milliarc second type, tens of milliarc second type scales in the center of our galaxy, the big surprise is that there's lots of stars there. And many of these are young stars, including this famous star S2 shown here, or SO2, which is the one with the 16-year period orbit that measures the mass of the black hole to be 4 million solar masses in the center of the galaxy, and won a Nobel Prize in physics in 2020. And so the data that are analyzed for that experiment look kind of like this. So here's a diffraction limited adaptive optics field from a single telescope showing the star S2 and Sagi star here and some other stars out here. And when you go to the interferometer data, the field of view is only this little white circle here. And on the right is shown then an interferometric image, the actual deconvolved source of just Sagi star now, the black hole. And then on top of a residual map, so a dirty beam, just to show that you achieve immediately much, much, much better imaging resolution. And the trade-off is that it's kind of hard to make images with 4 telescopes. But if your field is sufficiently simple, like here, one brighter point source than the other source than anything else, then you can still reconstruct nice images. Okay, and so this has been a real advantage towards detecting relativistic effects around the black hole from stellar orbits on timescales of months. But here I'm going to focus on what we can learn by tracking the motion of this emission region of Sagi star itself when electrons are transiently accelerated on timescales of minutes to hours. So this is an example of a Sagi star flare, again, from single telescope data, this time from Keck, from Tuan Do's paper in 2019. And what we see is that these flaring events from Sagi star, the infrared luminosity increases by factors of 10 or so, or in this really dramatic flare up to almost a factor of 100. And so the idea then is in 2018 with gravity, we were able to look at not only brightness changes like shown here, but also how does the centroid of this emission move over the duration of a flare. And what was seen is that here is showing on the left the X and Y centroid offsets as a function of time over 30 minutes during a flare, one example of 3. And what we see is continuous rotation of the infrared centroid in astrometry. So going from this red point here to orange to green to blue over the timescale of about half an hour during this flare. Okay, and the center of the motion that we infer is the pink cross, and it agrees, as far as we can tell, with the expected location of the black hole itself from stellar orbits shown in orange. Okay, and so if you just take the size scale here is in tens of microarc seconds, and so the implied velocity is about 20 to 30% of the speed of light at the Galactic Center. The size scale on Sky is about 3 to 5 times the Schwarzschild radius, and that is consistent with orbital motion around a 4 million solar mass black hole in the center. Okay, so this would bring evidence of the existence of the event horizon, or the mass that's contained within the orbit of the star S2 down from about 1,000 Schwarzschild radii down to about a few. Okay. Yeah, sure, Charles, go ahead.
Jason, how independent are these error bars? Are the errors from one measurement to the next?
Yeah, so the error bars are taken as scatter among shorter integrations. So I guess there's 2 things. So we correct for systematic terms, which could move all the points a little bit. There aren't many known that would move all the points a lot for technical reasons that I don't want to get into right now. But but I think to affect the position, say, of the pink cross relative to orange, then you could think of some systematic errors that do that. To change the motion on sky, you would have to think of a systematic which changes then rapidly, like over 10 minutes. So does that answer the question? So the error bars are purely statistical from binning lots of shorter samples. And the assumption is that we aren't aware of any systematics that would operate on short timescales like that.
Okay, thanks.
Okay, I hope that helps. Okay. So we saw this in 3 flares in 2018, and then the assumption is that, so the interpretation is that this is consistent with orbital motion. And so the picture you might have in mind then is, if you could resolve it, very sharp imaging with some artistic sprinkles added in, is something like this. So some flaring emission region shown here in red, and going around clockwise on sky. I would say it's a very interesting question because this is transient heating of electrons. All speeds close to the black hole are expected to be of order the speed of light. There's an interesting open question of where is this emission actually coming from, and is it actually orbital motion that we're seeing? But it's at least consistent. Okay, was there another question or no?
Yeah, I was going to ask about exactly that. That the assumption is it's carried around by orbital motion, and it's not like there's not a wave or something like that. Right? Yeah.
Yeah, I think that's open. I think this was taken as a consistency statement that this could well be orbital motion, and it fits in the sense of the size scale and the velocity would, if you infer a mass from that, would agree within sort of this factor of, I don't know, 2-ish level.
Yeah,
but
no, it's super cool. It's super cool. It's neat that you can then go, you can actually ask questions like that. So, yeah.
Yeah, I think the other statement I would say is if it turns out to be something else, I don't think that invalidates arguments about a black hole because something is making it rotate at the speed of light. But yeah, I think it's an interesting question. I would just say, if anything, there's a slight tension that the motions are fast the motions are fast compared to their slightly large sizes.
Right.
And so if there's a tension, it would be that something would be moving faster, would be rotating in sort of what appears to be a super Keplerian type way.
Yeah, got it.
I have a question.
Yes, please, go ahead.
If you really knew the flares were representing orbital motion, and you knew their distance from the black hole whose mass you could determine the spin of the black hole.
So to know the spin here, I think we would have to know what radius in units of the gravitational radius or the Schwarzschild radius our flares are supposed to happen at.
True, but I thought your image shows sort of
that. So in this artistic impression, we put it somewhere. I think we would need a physical mechanism to understand what number that should be in units of Schwarzschild radii.
But I thought your previous image had an XY plot showing the XY positions of the flaring material versus the centroid, i.e. you would know the radius distance from the black hole.
Yeah, that's right. We need to know to know a spin. We would have to assume, for example, you could try to assume this is at the innermost stable circular orbit or something. You would have to assume that.
No, you would know you would have to know the radius and the mass, and that would, given a period for the.
Oh, I see. Yeah. That's right. Yeah. So sorry. Okay, I understand the argument now. Yeah. So the radius is sufficiently uncertain that we cannot go that far.
Okay.
Yeah, thanks. Sorry for being slow. Yeah. So it's basically any spin would be allowed within the precision that we can make the measurement right now. Yeah.
Right. Thanks.
Yeah. Thanks.
So if I may interrupt one more time.
Yeah, please.
Okay. So what can you infer from this observation, the geometry of the accretion flow?
Yeah. So there's an interesting question. Okay, so there's an interesting question about what does it mean that the motion looks like it's in the plane of the sky mostly, right? So it doesn't look like a line, for example. At high inclination, relativistic effects would change that a little bit, but still, this looks mostly sort of like a pattern on the sky. So there's some question about what that means for the inclination. And I think we would favor then that we're looking, not exactly face down necessarily, but we're not looking like edge on at the accretion flow, if that makes sense.
Okay.
Yeah, so the inclination constraint, we would favor something like, I don't know, less than 50 or 45 degrees or something like that. There's also a constraint from the fact that the total flux is shown here in black, but over all the flares, we don't see that a certain position around the black hole seems to be brighter. So there's some constraint then on the Doppler beaming effect. And that would also favor a lower value for the inclination angle, that the material is not coming rapidly at us. Otherwise, we should see brightness changes which correlate with position.
Yeah, so the geometry is a Keplerian disk. Is that the case?
That's an assumption. Yeah, so we're saying that it's consistent with orbital motion if we're at Keplerian. If we're actually very, say, sub-Keplerian, then the tension that I mentioned gets worse. The motions appear to be slightly super-Keplerian, so they would not favor a very sub-Keplerian accretion flow. Okay, great. Okay, cool. So the second facility doing this is the Event Horizon Telescope that I'm sure many people have heard about. Illinois is obviously heavily involved in this. I just want to point out that this experiment uses premier submillimeter observing facilities from around the world. And so it's very large collaboration of a lot of people with twiddle numbers there, hundreds of people in institutes and countries around the world. And this is an out-of-date collaboration meeting photo now from fall 2018, just showing some of the people. And the other thing I would point out is that a week or so ago, they wrapped up the first new observations of the EHT in 3 years. This is very exciting. Dozens of people who deserve immense amounts of credit for going to remote locations around the world. And I think these pictures taken from the observing run kind of capture all the key elements as I understand it of EHT observing. We have lots of monitors in a control room, pretty pictures of sunsets and telescopes, very large hard drives with about a petabyte of data recorded at each station these days, and snow and ice. So we have all the critical aspects of millimeter observing. Okay, cool. And so the first imaging results from this new Event Horizon Telescope array were in the galaxy M87. Very, very different from the center of our galaxy in that the source M87 is famous for its relativistic jet seen at all wavelengths in the radio and optical where it had previously been observed. So it's just a nice set of images showing radio emission at low frequency on the sort of the size of the M87 galaxy here. And then zooming in says the interaction with surrounding gas. And then zooming in and you can start to see this mostly one-sided jet appear here from a VLA image at 1 gigahertz. And then zooming in even further to the core, seeing the sort of structure of the jet with VLBI. And the really interesting thing before the Event Horizon Telescope results were known, the big question a lot of us had was, what would we actually see? So the idea is that in the jet is that it's becoming optically thin and you're going to higher frequency. And so you're able to see further and further down into the core as we get higher spatial resolution. So we thought that maybe it should become optically thin at just about this 1 millimeter where the EHT observes. And so the question was basically, where should you land at the base of this jet? Should you actually land, should you actually land near the black hole, or should you land out at the base of a jet somewhere away from the black hole? And happily for all of us, what was seen is just a qualitatively different image than seen at all other wavelengths. We no longer actually see the jet, and instead we see this bright ring of emission, very similar to what was expected from the theoretical images that I showed earlier. And so the interpretation of this image is that, again, the emission that we see is set a lot by relativistic effects of Doppler beaming, which causes the bottom part to be brighter. The jet is pointing off this way. And so we expect this to be rotation near the base of the jet. And this part is then coming towards us. And so it's brighter. And the size scale here of the image compared to theory even lets us infer then the mass of the black hole in a new way. So again, bringing evidence of the existence of a supermassive black hole down to scales of at least comparable to the event horizon here. Okay, and so this nice comparison here is showing, use enhance on this left image And then maybe if you could zoom in, it would look like this theory image, something like this shown here, where again, you can see the shadow of the black hole feature in the middle. And then this is emission from mostly accretion flow and jet emission, and even where the photons orbit the black hole one or more times, the so-called photon ring feature here. And generically, if you take many of these different images and sort of blur them, reconstruct them to the imaging resolution of the EHT, which can resolve the emission remarkably, but you know, with not very sharp compared to the size of the event horizon, and then you get good qualitative match to all the features that are observed here. Okay, and so of course, mostly this is a great technical achievement by everybody developing instrumentation over decades, and the imaging work and data work here. But I also just want to mention that for MHD accretion theory, I think this is a really great achievement, because it means that we think we're on the right track, that the emission is really coming from next to the black hole. And now we can try to use it to learn about what's going on with accretion and jet launching right next to an event horizon. Okay, this is a really promising start for trying to use MHD accretion theory to understand real sources. Okay, so that's the good news. The bad news is that this was such a generic prediction of the accretion flow models and jet models that we have, the Sgr MHD models that we have, that it's very hard to tell different scenarios apart with one total intensity image like we had. So these are nice examples of very different physical scenarios that you might like to be able to tell apart. So retrograde spin, gas rotating opposite the spin with weak magnetic fields, zero spin and weaker magnetic fields, prograde spin and strong magnetic fields. And at least in these examples, once you blur them suitably, there's no obvious feature that stands out that lets you immediately tell these apart. Aha, it's that one and not this one. Okay, so this is very good because it gives us a lot of faith that we're on the right track here. But we need a better way to try to start learning about parameters of, say, the accretion flow. And that's what we will do using linear polarization. Okay, so I want to explain how this works. So the basic way this works is very similar. If you've heard about similar studies in, say, jets, for example, we're looking at synchrotron radiation. And so the emitted polarization comes out perpendicular to the line of sight and the magnetic field direction. And that means that the way a resolved linearly polarized image or map looks will depend on what magnetic field configuration is present in the emitting material. Okay, and so two examples from work by my former student, Alejandro Jimenez Rosales, are shown here. And the main thing I want to focus on is the case on the left for the sort of basic hypothesis of start out with weak magnetic fields. So meaning that the magnetic field is in a toroidal configuration, as I'll explain in a minute. And then if you just go through how this tick map gets set, the EVPA ticks come out in a radial pattern like shown here. Okay, so this is the how this comes about. This is basically just doing some late afternoon cross products here. We have a magnetic field which is wrapping around azimuthally, an observer looking down mostly straight down into the screen. And so then K cross B then gives you this radial pattern from an azimuthal pattern of magnetic fields and produces this map here. And the point is that to get something substantially different than that, which I'll explain in a little bit, you need some other component of magnetic field, some poloidal component of the magnetic field, radial or vertical magnetic fields to be important to get a different pattern than this one. Okay, and the reason this is so interesting is that this magnetic field configuration next to the event horizon should depend on the relative strength of the magnetic fields in the sense that we discussed earlier, that basically the weak initial fields pointing out of plane, so vertical or radial, will be dragged and sheared with the orbiting gas and will produce a toroidal configuration next to the event horizon. And so to remain poloidal in some different configuration is only possible if the magnetic field is dynamically important. And that's what we mean when we say strong magnetic fields. Can the magnetic field resist the pull of the gas and remain pointed in some different direction other than moving with the gas? Okay, and so a really extreme cartoon scenario would be drawn here, an analogy with a neutron star magnetosphere, basically, where if you accumulated strong enough vertical fields in the picture shown here, you could actually say truncate the accretion disk at some radius. Okay, so I don't think that we can currently realize this scenario, but this is something else you could have in mind for fields that are very, very dynamically important. Could point mostly like this rather than azimuthal. Okay, so I'm going to discuss how linear polarization from the two experiments can get at this question. Is the magnetic field dynamically important next to the event horizon? Okay, so in the first case, we're going to do the Sagi star flares with gravity. And here again, we do not resolve a linear polarization map, but we can calculate or measure a linearly polarized linear polarization information as a function of time during a flare. And the argument is that because we know our emission region is rotating around, we might be sampling different times of a background magnetic field as shown in the diagram here. And so the change in our polarization direction versus time would then tell us something about the magnetic field structure around the black hole near the event horizon. Okay, and so there was one particularly good flare for this. So this is a different flare than shown before. But here we have a double peaked flare in total intensity. And then what's shown is the linear polarization angle, which goes around once over the course of the flare. And as far as we could tell, the astrometric period is comparable to the polarization period. So they're basically the same. And if you think back to our weak toroidal field case, we should see two oscillations of the polarization angle per orbit, because for this radial polarization map, we should encounter both vertical and horizontal polarizations twice as the emission region moves around once. And that is not what we see. And so we interpret this as that some other component of magnetic field is required so that we only get one oscillation of the polarization angle over the flare. Okay, so this is evidence of strong magnetic fields near the event horizon in the Galactic Center. Okay, so for the last thing I want to talk about is the new M87 resolved polarization map in linear polarization. So we've taken our orange glowing image from before, and now total intensity is in grayscale, and the ticks are now encoded in direction of the EVPA, but also now color coded for the fractional polarization on the ticks. And this is again a large collaboration effort, but I did want to highlight the names of people that worked on the writing teams for the two papers that came out describing the data and imaging methods and then the theoretical interpretation. And I will focus on the theoretical interpretation because that's what I know enough about to say something about. Okay, so I want to show about the data is that, again, a tremendous amount of work went on in the collaboration in using qualitatively different methods to reconstruct the linear polarization map on sort of these micro arc-second scales near the black hole. And they produce very consistent, qualitatively very consistent results. So these are different methods going from clean methods, so classic methods in radio astronomy image reconstruction shown here, to maximum likelihood methods here, and full Bayesian fitting methods for fitting the polarized flux in pixels shown here. Okay, and I just want to emphasize, this is a really difficult problem because for one thing, there are instrumental error terms in polarization, which are different for each station. And each station of the Event Horizon Telescope is a completely different facility. So there's a huge amount of work involved here in figuring out these error terms and getting these polarized images to work. Okay, and then if you take a suitable average from different methods, then you can produce on each day of observations 4 images of the polarization that look like this. Okay, and so they look broadly consistent. There actually is a slight change between the first 2 and second 2 days. But for the purposes of today, I'm just going to try to give a basic idea of what we think this means total, so over the full range of what's seen. Okay, great. So looking at this image, there are 2 main things that stand out. So the first is that the EVPA pattern is sort of twisting around with the ring. not quite azimuthal, but sort of in an azimuthal pattern. And the second thing is that the linear polarization fraction is actually kind of low. So the fractional polarization at EHT beam scale, which again is this 20 microarcsecond type circle here, is only about 10% on average over the ring. And you could compare this to what's expected for synchrotron radiation, which locally should be something like 70%. Or if it was a uniform magnetic field with nothing else going on, might be say 50% at the scale of our beam. Okay, so something is depolarizing the emission somewhat, and the magnetic field pattern is twisting around. Okay, so the first statement is going through the twisting pattern and what it means. And I want to highlight some really great work that was instrumental in our interpretation and how to quantify these patterns, the fact that this pattern seems to be twisting. And that's an azimuthal decomposition of this tick structure. So with different moments around the ring. And it turns out that the second azimuthal moment of this decomposition of the polarization is equivalent to E and B modes in cosmology, if that's more familiar to you. Why I think this is such a powerful way to quantify the polarization pattern is because it maps really, really nicely onto the toy models that we were showing before for idealized magnetic fields near the black hole. So for example, the pure toroidal case maps onto a value of this second coefficient that we call beta 2 of 1 as a complex quantity. A radial magnetic field we didn't go over, but that would just be the whole pattern rotated by 90 degrees. So that has this value. And even the vertical case that I didn't really discuss that has this interesting twisting pattern maps pretty well onto a specific value of this coefficient too. So it's just a nice way to take a full image and measure a number from it to quantify the EVPA pattern. And the basic thing that comes out of this qualitatively is, again, that the pattern is sort of twisting around in the observed image. It is not the toroidal case shown here. And again, this suggests the presence of strong magnetic fields, a significant poloidal component to the magnetic field next to the event horizon, which we think dynamically important or strong magnetic fields. Okay, so that's qualitative result number 1 from what we see. Great. The second thing is depolarization. And that we Faraday lengths. So it turns out that the polarization pattern can also be modified by propagation effects by linearly polarized light traveling through the magnetized plasma and having its polarization angle rotated by the Faraday rotation effect. Okay, generally, if you think about this like from a background source traveling through the Milky Way, for example, or through a galaxy to try to measure the magnetic field, we don't think of this as depolarizing the source. It just rotates the angle. But what we think is happening is that this effect of Faraday rotation is happening internal to the emission region or close to the emission region, so that different pixels on the image get rotated differently and cancel out, and this can scramble the pattern. Okay, and so examples are shown here of if you take kind of a canonical model and give it a slightly lower density and higher electron temperature, which is not known a priori within this range. And here you get a very ordered polarization pattern where you would measure something like 50% at the EHT scale. And here instead you turn up the density a little bit and lower the temperature, and now the pattern becomes scrambled significantly from this Faraday rotation effect. Okay, and so we think that this effect actually helps us to measure the plasma parameters near the event horizon too, because basically the temperature can't be too large, or the Faraday rotation effect, which scales as density times field strength times TE to the -2, would go away. Okay. And the only other point I would make is that this effect, the strength of this effect, basically how many times your linear polarization angle rotates all the way around, is proportional to lambda squared. So we did not worry about this effect for the near infrared because lambda is so much smaller. And so this nice plot from Alejandra is just showing that in a set of these simulated images, Faraday rotation can bring the average fractional polarization on an image down from this 50 or 60% down towards 10% or so that we observe. But that's only possible if this effect becomes significant. Okay. And so as a concrete example from an M87 model used in the interpretation, I'm showing here images calculated on the top with Faraday rotation and all other plasma effects and relativistic effects, and on the bottom, which is the same, but just turning off the Faraday rotation effect. And the left column is showing this tick map, but if we don't blur it at all, just calculate it at very, very high resolution, and you can see without Faraday rotation, the ticks are very well lined up. And so then when we blur them on the right, the polarization degree on the image becomes much higher and much higher than what's observed. Okay, and if we include the Faraday rotation effect up here, then you can see that the ticks become scrambled a little bit. And then when we blur it to the Event Horizon Telescope resolution, this decreases the degree of polarization on the image down to something consistent with what is observed in the data. Okay, so qualitative result number 2 of our interpretation is we think that the depolarized image, the fractional polarization of 10% is constraining the plasma parameters. So it's telling us that the electrons are not very relativistic, and in turn helps us in a minute measure things like what is the accretion rate on M87, for example. Okay, so those are the 2 qualitative results. And I think these are very useful in guiding our interpretation and understanding qualitatively what types of effects we should worry about in the interpretation. You may have also noticed that those 2 results back to back are sort of in tension with each other. So we think that I'm claiming that we can measure event horizon scale magnetic fields from the linear polarization because it's emitted perpendicular to the magnetic field. But then I'm saying that it's rotated all over and scrambled by Faraday rotation. Okay, and so those would seem to be in conflict with each other. And because we think those effects are important, and also the turbulence of the magnetic field is important. If the magnetic field is just really, really scrambled on small scales, that could also depolarize. And relativistic effects can be important too. And so the main way that we can realize all these effects self-consistently is to use the Sgr A and M87 models that I was describing earlier in the talk. Okay, and so that's what we did to try to make quantitative comparisons to the data. Okay, and so what's done for this is people in Illinois generated a huge library of images like the ones that I described earlier in the talk, 72,000 images spanning critically this weak or strong magnetic fields, but also parameters describing the uncertain electron temperature, temperature of the radiating electrons, black hole spin, and other parameters. And so here, for your viewing pleasure, is the updated one of these montages showing, not just the total intensity images now at their native resolution on the left and blurred on the right, but also with the white polarization ticks now added. Okay, and so what we did is we compared these derived metrics describing the twisty pattern and polarization degree from the data to those from theoretical models, just to understand basically whether our qualitative conclusions are borne out in a detailed comparison or not. Okay, and so I won't go through details on what was done, but we basically used integrated properties related to this beta 2, which is telling us what is the sort of rotational structure of EVPA, and related to the degree of polarization on the image. And I just want to show a comparison that this is a couple, so most of the models do not pass this comparison as expected, but of those that we say pass, that could match the data, even though we didn't fit for the detailed structure of the polarization map, or does it look like the image? I just want to show that some of these examples actually do look a lot like the image that we observe on the left. Okay, and the vast majority that fail are often either in the category of far too polarized, far too depolarized, Faraday rotation is too strong, or here the EVPA pattern is also wrong. This is a toroidal field dominantly, and so the pattern is radial here. Okay. Great. And so what we did is we used 2 different methods to try to score basically per model, how well did each of them do? And what can we say about the likely accretion parameters, assuming that these models are correct. And the main result of this comparison is that the strongly magnetized models are favored over the weakly magnetized ones. So these are 2 plots of 2 different methods. Some version of how many image passed is on the left. or a relative likelihood score on the right. And far more of the strongly magnetized models pass by each comparison. And so we think that this qualitative conclusion that the fields near the event horizon are dynamically important seems to be borne out in a quantitative conclusion, even accounting for effects of Faraday rotation and turbulence. Okay, great. And so then the last thing to show about that is basically to show how this helps us constrain the parameters of accretion onto M87. So we can here plotted on the left in particular is a distribution of the mass accretion rate onto the black hole as we had it in 2019 from just total intensity data in blue. So you can see here there's about a factor of 1,000 range in the mass accretion rate allowed onto the black hole. And once you use the linear polarization information as well, this collapses fairly well to an estimate. So we can say that twiddle, the accretion rate on the black hole is 10 to the minus 3 solar masses per year. So expectedly far lower than for quasar. And also interestingly, much less than the Bondi accretion rate inferred on large scales from X-ray measurements. So this would be a similar situation at the Galactic Center where a small fraction of the available mass that could accrete is actually making it down to the black hole. Okay, and we also now, well, the question mark is for George's benefit. We think the radiation may be mostly produced by inflowing gas, meaning that it is not obviously in the walls of what will become the jet on larger scales. It seems to be more attributed to the accretion flow onto the black hole. Okay. So just the last point is basically that we will continue to test this hypothesis and learn more. So from future observations, both just repeating the measurement in time, we expect to see, like in the movie I showed at the very beginning, a highly variable polarization whose average properties are maybe not so different from what we see now, but with fluctuations that will tell us more about the accretion physics. And also going to different frequencies. The Event Horizon Telescope is gearing up to observe at somewhat higher frequencies. And the Faraday rotation effect should decrease at higher frequencies. And so, for example, I like this example shown here where this spot over here is depolarized at lower frequency, but then becomes more polarized as Faraday rotation weakens at higher frequency. And in particular, doing some kind of a Faraday rotation map across the images should help to test that hypothesis that that's what's causing the depolarization, since it has this lambda square dependence. Okay, so to summarize, we can now resolve event horizon scales around at least these two massive black holes, Sagi Star and M87, and using two experiments, the EHT and gravity. I tried to convince you today that linearly polarized images on horizon scales are really great probes of what magnetic fields are doing. So we can actually zoom in towards the event horizon where accretion energy is released, where jets are launched, and try to just look at what the magnetic field is doing by studying these linear polarization maps. And there are two ways to measure these with the two experiments. And each of them, interestingly, in different sources, seem to show first evidence of dynamically important magnetic fields on event horizon scales. So that will be a really interesting, that would have interesting implications for accretion, and will be interesting to test more with future observations. Okay, so thanks a lot for your attention. I'll stop there.
Okay, thank you very much, Jason. So I think we should have questions. So Stu, you can go ahead.
Yes, beautiful talk. I have a question. As you know, many models, most models with strong magnetic fields accreting out of a black hole, including our own calculations, show a jet that is characterized by a helical magnetic field structure emanating from the poles going out to large distance and confining the outward stream of gas along the walls. The question is, will polarization studies be ever able to validate that picture? Or is it, as you said toward the end of your talk, most of the emission not coming from the jet, and hence we may never be able to do that validation?
Yeah, thanks for the question. Yeah, so I guess two things on that. So one is that radio VLBI studies, so at somewhat worse resolution, but probing frequencies further out, so say in M87, that they are studying the emission from some part of the jet. And so those studies try to infer properties of, say, helical magnetic fields. So I think the two measurements I'm aware of is that you can try from polarization to measure things, especially about how the Faraday rotation changes. You can try to infer the presence of a helical magnetic field, and that's been done in a couple of, I think, more luminous quasars like 3C273. And the other thing, what was I going to say? And I think also in the results that I discussed today, I think one interesting possibility for the flares, one alternative possibility for the flares from the Galactic Center, is that maybe that is actually close to the base of a jet. So it shouldn't be strongly beamed at us, but otherwise we don't actually know. So if it turned out that the flaring events are following, say, the base of a jet, then you may be able to learn something, say, from how the polarization signature changes as you go up, since toroidal fields are thought to become more important with height above the black hole.
Great, thank you.
And Sheen?
Yeah, thank you. Wonderful talk. Incredibly exciting. And I should say that it's very rare to see this type of direct comparison between, state-of-the-art observations with, first principle calculations. So it's really nice to see the field developing. So my question is, it's really interesting. These two sources kind of represent the two boundaries of, in terms of the mass range of the supermassive black holes. But unfortunately, as you already mentioned, right? So they both of them are at the extremely low attention end of the accretion. So I'm wondering about the implications of your result in terms of the overall understanding of the the growth and the evolution of supermassive black holes. Like, for example, for the magnetic field to be dynamically important, right? So is it can we say something about the long-term evolution of the dynamic field? Has it always been important, or is it just because the state that we catch them at these two particular sources in the parameter space that they it's important? So how do we use the results to understand the overall evolution?
Yeah, thanks. It's a great question. So yeah, I think that in particular, this accumulation of magnetic field should operate very differently depending on the accretion state. So as you said, the two objects where I presented results today are very sub-Eddington, and the accretion flows are expected to be hot and thick, and that makes it easier to drag in magnetic fields from the environment. So that's one thing that I think it's still somewhat open how this operates at high luminosities in a more like a quasar, for example. And that the actual accumulation of magnetic field may operate differently. And also the feeding source should be completely different. So the available magnetic flux that you could drag in to make strong fields could be different in those systems. Certainly in the Galactic Center, this is thought to be feeding from stellar winds of O stars and Wolf-Rayet A stars very close in. So that mechanism of feeding should be very different from a quasar. So I think both those things probably you'd want to address before trying to apply this in general to the full population of black holes. So even if it holds for two sources, then you wonder, does it hold for all the sub-Eddington sources? And even if you say then it definitely holds for all the sub-Eddington sources, extrapolating that to quasars is different. But I do think it's an interesting, it's an interesting question theoretically. If we think that MHD accretion can explain some of these systems, then what might we expect to happen in different environments? and maybe there are similar observational probes. I'm not really sure. Yeah.
Okay, so Brian will take the next one, and then after that, I have a question. So Brian, go ahead.
Yeah, so Jason, thanks. Really beautiful stuff. So I'll contain myself and just ask one question. So so just to go, the stuff at the beginning about the infrared observations of the flare, I hadn't seen that before. That's really, really gorgeous. So just a very naive question. Was that I guess that was a particularly bright flare that you were showing us?
Yeah, so there are a few challenges that limit when those measurements can be made.
Right.
So there are 3 flares from 2018, which is not a coincidence. That was the year of the closest approach of the star S2 to Sagi star.
Okay.
And so during that 1 year, there was basically a direct interferometric binary source. So when you looked in the infrared, you saw 2 sources. Whenever Sagi star was bright, you saw 2 sources. And there's just a remarkable thing that the brightest flares from Sagi star are comparable in the infrared brightness to the star S2. And an equal brightness binary is really great for doing precision measurements. Anyways, your interferometric observables are basically doing 0 to 1 oscillations. And so anyway, that was a very good year for doing these flare measurements. And as I mentioned earlier, the systematics that you worry about are lessened because the 2 sources are so close together. A lot of the systematics scale with separation, and so that they were even smaller. So there are a lot more flares observed with gravity, is I guess what I would point out, even very bright flares, especially from 2019. And it just remains a challenge for making that same precision of a measurement and accuracy of a measurement when the star was much further away, and so it was not in the field of view at the same time. The instrument can make this measurement, but there are different systematics related to how you have to do it, and that remains a work in progress to get those data out. So we would hope to have more flares. We do have more flares. We'd hope to have more astrometry, but yeah, it's a slightly different problem. So sorry, this maybe ultimately answers your question. But yeah, the observations are only possible when Sagi star is sufficiently bright. So just as a signal to noise issue,
yeah, I see.
We can get astrometry, but it scatters, far beyond the scales we're talking about, and consistent with 0, and also is more challenging in other years than 2018.
Got it. Thanks.
Okay, so I do have a quick question. Then Charles has his hands up. So I guess Brian's question, your answer to Brian's question kind of partially answered my first part of the question, is the reason that you don't use gravity to observe M87 is because the source is too faint, and you have to have a flare like a Sagittarius star to be able to observe it with astrometry.
Yeah, so let me just advertise on that, the one of the last bullets on this slide, that combined observations can be made of Sagi star, and I think that'll be really interesting for if Sagi star in the EHT data shows something similar coming from horizon scales that we think we understand and so on. It would be really exciting to do this type of polarization measurement to try to see, this would help as a test. Do they look similar? Do they agree with each other? And I think also it could help to try to figure out where these flares are coming from. Does it look like it's the same component as the submillimeter emission? This has been done for a long time in total flux. There are possible relations between total flux in submillimeter and infrared flares, but they're kind of tentative and unclear. And so hopefully by spatially resolving the emission, we can get at a lot of that. So that's something that I'm particularly looking forward to.
Right.
But you're right, M87 is not observed with gravity so far. There's actually an upgrade of gravity in progress. So maybe ultimately it'll be possible to observe gravity observe M87 with gravity. There, I think you'd have to ask, what do you actually expect to see in the infrared?
Right.
And is there a source that moves on interesting timescales there? Yeah.
So the second part of my question is, gravity has resolved astrometrically the blowdown region of some bright quasars and AGN. So any polarization results from the magnetic fields in the broadline region?
We have not dared to do polarization in the broadline region stuff. Those broadline region measurements are actually even more difficult than the Galactic Center stuff that I showed today. So the equivalent kind of angular scale that we're getting at, this measurement is done by phase referencing the emission line of a quasar to its continuum. So the continuum is hot dust in the infrared coming from the component called the torus, whatever it is. And then we basically look for position shifts between the emission line as a function of its wavelength and the continuum. And those, to make detections there, we reach sort of micro arcsecond, 1 micro arcsecond or so type precision to make those measurements. So yeah, we haven't dared yet do that, splitting the light again in polarization. But I would actually be interested if you expect to, like, what type of a signature would you actually expect to see? I would be interested in talking about that more. Maybe it's worth trying, basically.
So Charles.
Yeah, so Jason, you kind of already answered my question by saying that there was an upgrade of gravity underway. But I'm just wondering what the future of gravity is and similar instruments, or if there will be any similar instruments in the future.
Yeah, so
what will it be able to do better and why?
Yeah, so the idea is to push for much higher sensitivity. So there's already been an upgrade of detectors, which helps a lot, especially when we make spectra. So like for the quasar case I just mentioned. And then they basically eventually want to upgrade the adaptive optics systems to put laser guide stars on all of the 4 telescopes. So again, especially for the AGN or quasar science cases, but probably also for the Galactic Center, we need to have adaptive optics to get flux into the instrument gravity, which can then be interfered as an interferometer. And so upgrading the adaptive optics can improve the sensitivity quite a bit just by increasing the Strehl ratio of increasing the adaptive optics performance. And so that and a variety of other improvements are being made. The other one is to go to a wider field of view, actually. The way that the Galactic Center experiment works is by referencing to a bright star that's within 2 arcseconds away from Sagi star. So that type of science case works in the Galactic Center and not many other places on the sky. So the idea is to go to a wider field of view, which would then let you do a similar type of off-axis measurement, again, kind of like adaptive optics, but over a much wider part of the sky. So to cover more sources with really sensitive interferometry.
Thanks.
Okay, any more questions? Okay, great. In that case, let's thank Jason again. Give him another round of virtual applause. So Jason, if you can have some more time to stay around, Brian has some additional questions that he might want